Okay, in this video I'm going to do an example problem of synchronous time division multiplexing. And in this problem we have 12 input signals, each with a data rate of 2 megabits per second. We're going to do bitwise interleaving, and we're going to use 2 framing bits per frame. And so let's go ahead and do this. We're going to make a sketch first, and the inputs have data rates of R1, and there are 12 of them into the multiplexer. 1, 2, 12. And in this frame now, we're going to have a bit from source number 1, then a bit from source number 2, etc., then a bit from source number 12, but then we're going to have 2 framing bits. Okay? And so what we're going to do is we're going to first of all assign little n is equal to 1, and this is, if I look at the equations for the synchronous TDM, we have the number of input streams is big N, the number of bits per stream in a frame is little n, so bitwise means little n is 1, bytewise means little n is 8. And then we have our data rate and period for one of the inputs, and data rate and period for the multiplexed stream. We also have the frame rate and frame period, and then the size of the frame and f, and I'll try to use those variables. So the size of the output frame and f is the number of bits from each source in a frame times the number of sources plus the number of framing bits. So big F is 2 here. And so we have little n is 1, big N is 12, and we have F is 2. And so we get 14 bits per frame. Okay. The frame rate is easiest to calculate by saying it is the bit rate of one of the input sources divided by the number of bits from that source or from any of the sources that's in the frame. And this equation is given above here. The frame rate is R1 over N. And that's because, so for example, in our case, when N is 1, in the time it takes for one bit to arrive from one source, the same simultaneously a bit arrives from all the other sources. And so in that amount of time we've got to create a frame and send it. Okay, so the frame period is equal to the bit period when little n is 1, and so the frame rate and the input source rate are the same as well. If little n is 8, then the frame rate is 1/8 of the input bit rate, because we have to wait for 8 bits from each source to get there. Okay? If you think about it, I hope it makes sense to you. R1 here is 2 megabits per second, and n is 1, so the frame rate is 2 mega frames per second. Okay? The output frame period, TF, is simply 1 over RF, 1 over 2e to the 6th, which is 0.5 e to the minus 6, which is 0.5 microseconds, or 500 nanoseconds. Okay? The output data rate in bits per second. This is a little bit more complicated when f isn't equal to 0. Because now our frame rate is, or our bit rate, the output bit rate is R tot. In our notation here, R tot is the bit rate of the output. It's going to be a little bit more than the sum of the input bit rates because of the framing bits. And so what we've got to do then is we've got to say, well, it's still the number of bits per frame times the number of frames per second. And so we can use this equation even if f isn't 0. And so, and you'll see that I'm using 14 bits instead of the 12 had I not had framing bits. And that's where the extra speed, extra data rate comes in. So I got 14 times 2 megaframes per second, which is 28 megabits per second. And that's faster than the 24 megabits per second that we would have if we had multiplexed 12 2 megabit per second signals together. The percent of the frame that is data bits, well, 12 out of those 14, and 12/14ths, I can calculate it here. It's 86%, roughly. Okay, well, here's the solution to that one, bits per second, and I hope that helps. We can also calculate the R tote using this equation, but I'm not going to go ahead and do that right now. So, hope this helps.